here we will continue to try to find AN. So if you look, you'll notice before we had 2c over L, but you'll notice both terms in the integration by parts had L over n pi. So I'm going to pull out the L over n pi out of both terms like that. So we're really going to end up with 2c over n pi as our constant term. And then that is all times those two terms. So all that's left of the first one is minus x cosine n pi over Lx. And that's evaluated from 0 to L. But I'm going to go ahead and do the integral and then evaluate everything from 0 to L. So on the integral, we pulled out our L over n pi. So it was the integral of cosine n pi over Lx dx. Let's see, cosine integral, cosine goes to sine. We have to multiply by yet another L over n pi. So it becomes plus L over n pi. And then it became sine when we did the integral n pi over Lx. And that is evaluated from 0 to L, so both terms are evaluated from 0 to L. So I think we're in good shape now. So let's see. So let's do the evaluation then. It equals 2c over n pi times, let's see. So when we evaluate this at L, we get minus L times the cosine of n pi. Let's see. So we can't simplify. So the cosine of n pi you can't say is 1. No. The cosine of n pi includes the cosine. Yeah, you can't just say it's 1 because it can also be negative 1. So you actually just leave that the cosine of n pi. Minus L cosine n pi. And then this term is 0, right? You plug in 0, you get 0. So that's minus L cosine n pi. And then we can do this term. And here, when you plug L into there, you get sine of n pi. And that's always 0. There's no plus and minus about it. That's always going to be 0. And when you plug in 0, that's always going to be 0. And there was another 0 in here. This second term, of course, was 0. So of all the 4 possible terms, the only one that works out is when you have an L right there, and it's minus L cosine n pi. So you can see, actually, that the AN comes down to something not too complicated. It's minus 2CL over n pi cosine of n pi. Correct? Yes, that is correct. So if you write the function y of x equals an infinite number of sinusoids, and here you put minus 2CL over n pi cosine n pi times the sine harmonics n pi over Lx, and you add up infinite terms, you'll make our little line. And just to make sure that's the case, I've plotted a few of them here. So let's see this about right there, and this side about right there. And let's have a look at some of these. So here's a plot of that function, and it's just the first term. N equals 1 term, and of course it's just a sine, right? Because the first term, the AN gives you some amplitude, but that amplitude is multiplying a sine. It comes out negative, so it's useful that the amplitudes can flip the sinusoid up and down, right? But anyway, that's the first term. So when we add a second term, we see, okay, it's maybe starting to look a little bit like a line. This side is getting a nice slope. This side is coming down very hard. We had a third term, and now you can see more and more. This must be our line, right? So third term, fourth term, fifth term. And now you can see a line, but it's not really making a line, right? It's making a sawtooth pattern. And we didn't ask for a sawtooth. We just asked for a line with slope C. But when I plotted these, I set L equal to 1, and I set C equal to 1. So we're looking for a line with slope of 1, but remember, just between 0 and 1. So when you use a Fourier series to make a shape of a function, it really only makes it on the domain that you use. Outside the domain, it'll usually repeat it or flip it upside down or do something like that, right? So that's what it's done here. This is the domain of our problem. From 0 to 1 is 0 to L on the x-axis, and 0 to 1 is 0 to 1 on the y-axis, and the slope is 1. So it is working its way towards, as we add more and more terms, a sloped line that looks like that. But if you go plot it outside the domain, it does other things. In this case, it makes essentially a sawtooth. So you can see that it is actually working, and as you add more and more terms, it adds them in just the right way, with just the right amplitude and just the right phase flip, positive and negative, to give you the line you're looking for.